Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is partition the array, and it is a hard level problem. So I was not able to make the video in the morning because I had some test in my college, and that is why I'm making it right now. So let us quickly discuss the problem statement. The problem says that we have been given an array of n integers, and the task is to partition the array into 4 non-empty contiguous subarrays. So we have to divide the whole array into 4 subarrays, and they should be non-empty, right? And we have to do them such that when we calculate the sum of p, q, r, and s, we will be denoting them as w, x, y, and z, right? Now we have to find the smallest absolute difference between the maximum and the minimum among these values. So like the problem statement itself is a bit complex, so I'm going to explain you with the help of some test cases. So we have this particular test case here, right? So what do we do now? We have been given an array like this: 4, 2, 2, 5, and 1, right? This is our array. So we have to divide this particular array into 4 subarrays. So in this particular case, it has been divided in this particular manner. So this is the first, second, third, and fourth subarray, right? We don't have to leave any element, right? So this is very important. All of the subarrays should be non-empty. That is, they should contain at least one element. The second condition is, right, after we do take them, no element should be remaining, right? That is what they mean when they say contiguous subarrays, right? So this is together, and there is no empty space in between. Now the second thing is, we have these subarrays. Now we calculate the sum of all subarrays: 4, 4, 5, and 1. So this is the sum of this particular subarray. This is the sum of this particular subarray. This is the sum of this, and this is the sum of this. Now we have to take the maximum and the minimum value among these 4 values. So the maximum is 5 and the minimum is 1, and the difference is 4, right? So this is the difference that we have to find. Now we have to divide the original array into such subarrays such that when we calculate this final value, this should be minimum, right? Among all configurations that we can divide the array in, this value should be minimum. So this is our task. Now whenever this is a very popular thing, whenever you want to divide for example anything, so in this case this is an array, but whenever we want to divide something into n number of parts, right? So for example, if I wanted to divide this array into n parts, and in this case it was 4 parts, so how many points do I need, right? Or how many lines do I need, or how many at how many places I need to break the array, or any particular thing. So to divide this particular array in n parts, I need to make n minus 1 lines, right? Or I need to divide this particular array from n minus 1 places. So if I make the first division here, second division somewhere here, and the third division somewhere here, so you will see that this is the first part, this is the second part, this is the third part, this is the fourth part, right? So I'm trying to give you an intuition of how you can think to solve this particular problem. To divide anything into n parts, you need at least n minus 1 points, right? So in this case, we wanted to divide the array into n parts or 4 parts. So in case of 4, we needed 3 lines or 3 pointers, we can say, right? So there is one thing for sure, that to simulate the value for all the subarrays, like to simulate the answer for all the subarrays, we need at least 3 pointers. Now the second question is, how do we manage these 3 pointers? So let us first discuss some brute force approach to solve this question. So a simple brute force solution would be to take 3 pointers I, j, and k, right, traversing all of them from 0 to n, right? I'm not taking the specific values, because when you try to implement this, you will have to make sure that each subarray has at least one value, right? So the exact specifics would be different, but let us just discuss it, that we have to traverse all the 3 values from 0 to n, right? So it would be an n cube solution, right? This is a simple brute force approach, that you can take 3 pointers I, j, and k such that you traverse them through the array, and for each value of I, j, and k, you will get some subarrays. So the first subarray can be from 0 to I, let's say. The second subarray can be from I plus 1 to j. The third subarray can be from j plus 1 to k, and the fourth subarray can be from k plus 1. So there is j plus 1 from k, and the fourth subarray can be from k plus 1 till n minus 1, right? So these can be the 4 subarrays when you take some values of I, j, and k, right? These will be the 4 subarrays that are formed. Now, this solution would obviously not work because in this case the value of n is 10 raised to the power 5. So we need to think of something different. Now I can what I can do is, if I have some array like this, I can take the middle pointer j and start placing it somewhere. So I can place it here, 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 and I can place it here, right? So let's say I placed it in the middle position j here. Now among the left subarray, I want to find a pointer I such that I want to minimize the difference between the maximum and the minimum value, right? So how do we form the maximum and the minimum value? The maximum and the minimum value will actually be formed by the sum of this particular subarray and this particular subarray, right? So I want to place the pointer I such that the sum in the left subarray and the sum in the right subarray are as close as possible, right? So how do we solve this? What we can do is, we can maintain a prefix sum array which will store the sum at any particular point I, right, from 0 to I. Now I know for any point I will know the sum of the left subarray, sum of the right subarray, and since this is the prefix sum, the value will be monotonically increasing, and hence I can do binary search on it. So what will be the criteria of binary search? The criteria will be like the sum, let's say the sum of the left subarray, this is the sum of the, let me write it properly. So I denote the sum of left subarray should be less than or equals to sum of right subarray, right? So if the sum of left is smaller, then I can move my pointer to the right. Why? Because this will increase the sum of the left subarray and decrease the sum of the right subarray. But if the sum of the right subarray is smaller than the sum of the left subarray, then I can move my I pointer to the left, so that it will decrease the sum of the left subarray and increase the sum of the right subarray, right? Now we want these values to be as close as possible. That is why we will be continuing this loop till when sum of left is less than equal to sum of right. Whenever this is true, I try to move my pointer to the right. Now obviously there will be some value for which, like for example, the left subarray is 10. This is the sum of the left subarray, and the sum of the right subarray is let's say 15, right? Now there is some value 5 which is currently present in the right subarray, right? Now if I want to extend my value of this particular left subarray by one more element, so this will become 50 and this will become 10, right? You see that the sum of this particular subarray will get increased by 5 and the sum of this particular subarray will get decreased by 5. Now in this particular case, the initial difference between the maximum and the minimum value would have been 5, and the difference in this particular value would also have been 5. Now there might exist some case, for example, the sum of the left subarray is 20 and the sum of the right subarray is 30, and the next element that is the first element of the right subarray is 5. Now if I try to include this particular element in the left subarray, it will become 25 and 5 will be subtracted from here, so it will also become 25. Now you see, by just adding one more element to the left subarray, initially the difference was 10, now the difference is 0, right? So this is what I wanted to show you. Even if you do binary search, our main criteria will be this particular thing. But once we have got the position of the pointer L or of the pointer I, we can also make one check on I plus 1, because there might be a condition where the I plus 1 pointer will be giving us a better answer, right? So this is what I wanted to show you with this particular example. We need to really take care of this, that if I am getting the answer I where sum of left is less than equal to sum of right, I also need to check I plus 1, right? It might give me a better answer. So now what happens is, similarly for the second part or the right subarray, I am maintaining a pointer k, and again I'll be doing the same binary search, and I'll be finding the sum of left, sum of right. I will try to minimize the difference between the maximum and the minimum values. And by what do I mean by minimizing? I mean that I will be trying to make both of the sums as close as possible. Similarly, when I will get a pointer k as an answer where sum of left is less than equal to sum of right, I will also check at k plus 1, right? Because it might give me a better answer, right? Again, when I'll get so I'll be getting a pointer k here, and for all values of j from traversing from the left side to the right side, I'll be doing this. I'll be finding I and k, right? So this will be my solution. Now, one very important thing I wanted to tell you, that if I have 4 values like I plus 1, k and k plus 1, right? So for each of the j's, I'll be having 4 values I plus 1, k plus 1, right? So I will have to like test all possible combinations. The first combination will be I and k. The second possible will be I plus 1 and k. Third combination will be I and k plus 1. And fourth combination will be I plus 1 and k plus 1. So I will have to test all of these 4 combinations to find my best answer for any of those j, right? I need to take care of this. So this was all about the solution that I wanted to discuss, and I know like this question is a bit tricky, and even the binary search is not that simple. You'll have to think of this particular case when I plus 1 will be giving me a better answer than I, right? So you'll have to take care of this, and there are certain implementation details as well which we will discuss while having a look at the code. So first, let me quickly summarize what I just explained in the solution. Now the first observation when you read this question that you can make is, for dividing this array into n parts, and that in this case the n was equals to 4, I want to make three partitions, right? I actually want to break the array from 3 positions. Now I can treat these 3 positions as 3 pointers. So I have my 3 pointers I, j and k. Unfortunately, due to the constraints, since the value of n is 10 to the power 5, I cannot brute force through my solution. Otherwise, it would be an n cube solution, and that would definitely give me TLE. So what I instead do is, I just like brute force through one value, and that is j, that is the middle value. So I traverse from the starting to the end of the array using the value j. Now for the remaining values I and k, what I do is, first of all we'll discuss about I. I know that I can be from anywhere between 0 and j, right? So I just do binary search, and during the binary search, my primary task is to make, since using I'll be dividing this array into 2 subarrays. So my primary task is to make the sum of the left subarray as close as possible to the sum of the right subarray. So I'll be doing a binary search till sum of left is less than equals to sum of right. Right. This would be my main binary search condition. Right. I'll keep moving to the right while sum of left is less than equals to sum of right. Now, if I've got a condition like this where the sum of left subarray is 20, sum of right subarray is 30, right? And the first element in the right subarray is 5. So let me just write the test case as well. So it can be like 10, 10, 5, and again 10, 10, 10. So the sum, it should be 5 here, right? So you see the sum of the right subarray is 30 and the sum of the left subarray is 20. Now the difference between the left and the right subarray would be 10. But if I add the sum of the left subarray is less than the sum of the right subarray, right? So what if I include this particular value, right? What if I include this particular value in my left subarray? So it will be 25, and this will also be equal to 25. So in this case, like this was not a very apt test case, because in this case both of the values are coming out to be equal. But there will be also some cases where the values will be like this, 26 and 24, right? And it would be a much better answer than the previous value. So we also need to check if we are satisfied with the condition that sum of left is less than sum of right. For some value of I also need to check for I plus 1, right? This is the most important step of this particular question that we need to check. So there will in this particular case both of the values were equal, but there will also be some cases where the left value will become greater than the right value, but still the difference between them would be smaller as compared to the previous iteration. So if I do the same thing for k, again I'll have k and k plus 1. So for each value of j, I'll have 4 values I, k, I plus 1 and k plus 1. So for each value of j, I need to test all the 4 combinations I and k, I plus 1 and k, I and k plus 1, and I plus 1 and k plus 1. So it is very important to check all the 4 conditions, so to find my best answer for every of the j, and j will be starting from the first position to the last position, we'll be moving our j pointer. So like right now I'm saying starting from the first position till the last position just for the sake of simplicity of understanding, but when you actually implement it, there will be many changes. J will start from some specific value and end at a specific value. It will not start at the first position, right? So we will discuss this smaller details while looking at the code. So let me just show you the code for this particular question. The code is also a bit long. I want you to bear with me on this particular question. So what I've done is I've created a prefix vector, and I just calculate the prefix sums of all the values, right? So this is very simple. Now I've created my best answer as 10 is power 18, and I've created my function find sum, which will give me the value of the summation in any range left to right. If I pass it left to right, it will give me the sum of the values in that particular range, right? So this is my find sum function. So it is very simple. If left is equals to 0, I just return prefix of right. Otherwise, I just return prefix of right minus prefix of left minus 1. So it will give me the answer in the range from left to right, right? So this is very simple. And now what I do is I start the value of I from 1. So this is actually the j pointer. I have named it I here, but it is actually the j pointer. So I am using the value from I from 1 to n minus 2. Now we will discuss why it is 1 and why it is n minus 2. So let me just show you here. So what I have actually done is, so if this is my array, this is my 0th index 1, 2, 3, 4, 5. This is n minus 1. This is n minus 2. This is n minus 3. Right. This is enough for us. So I am starting the j from this particular value. Why? Because at if I'm talking about j, I'll be including all the values till here, right? If I'm at if for the first loop, if I'm maintaining a pointer j, I'll be taking all the values till that particular pointer, right? So I'll be left with at least 2 cells here. Remember that whenever we are making j, we need to divide this particular subarray into 2 halves. So obviously I will need at least 2 values here, right? Similarly, I'm only going till less than n minus 2, so that when I include these values together, I'll still have at least 2 cells here, so that I can divide this array into 2 halves, right? So just to make sure that I have at least 2 values on the left as well as on the right, I am making this loop run from 1 till less than n minus 2. So this is the only reason why this loop is working like this, right? So these are the little implementation details that you have to take care of, and I'll be discussing the same thing while discussing the code. Now I initialize my low and high. So low is initialized with 0 and high is initialized with I. Again, the same thing. Whenever I am taking a particular index, I am assuming that the current subarray will run up to that index, right? So it will be including that index. So the kind of binary search I am doing is called invariance technique, where I assume that low will always be the answer. Low can always be the correct answer, and high will never be the correct answer. So how is this true in this particular case? Let us see. So if I have some array, let's say this like this. So this is the pointer j, and I want to find some pointer in between, right? So I want to find some pointer I in between, such that we want to minimize the difference between the left and the right subarray. So what we do is, for example, the pointer that I am going to use should never be equals to j. Why? Why should it be never be equals to j? For example, if I make my pointer here, all the values till here will be included in the left subarray, and the remaining values will be included in the right subarray. So that is why I want to leave at least one empty position for the right subarray, and that is why I am trying to make my answer never reach j, right? So in this invariance technique, high is equals to I means that I will never be the answer for this particular binary search, and 0 can always be the answer, right? Why 0 can always be the answer? Because if 0 is the answer, then my left subarray would look something like this, right? And I need at least one value. So like for everything there is a reason, and the reason is very specific, and you need to take these values very carefully. So in my technique, of binary search, like the low value will always be true and the high value will always be false, right? I have to maintain this invariance. So that is why I have taken these particular values. Now I just do simple binary search and just find some function I've already explained. So what I'll do is I'll find some between 0 and mid. So this is the value of mid that I'm calculating, and this will be the left subarray and this will be the right subarray. So this, if the value of the left subarray is less than equals to the value of the right subarray, then I'll assign low to mid, otherwise I'll assign high to mid, right? Again, I just when I've done this, I find my answer a value of p and q. P will be from 0 to low and q will be from low plus 1 to I. Now, as I have discussed, then that for every value that, for example, in this case it is low, right? I also need to check for low plus 1. So I'll be storing that value in pp and qq. So whenever low is less than I minus 1. Why am I doing this? This is very important. When low is less than I minus 1. So for example, if I have to check for one greater value. So let me just show you. So I have written low is less than I minus 1. And in the case, I have considered j to be I. So that I is actually j. So I want to make sure that my current value of low is less than j minus 1. So if this is j minus 1 would be this, and I want to make sure that the current value of low is less than or equals to 2, right? Why? Because if I want to check for 2 plus 1, if I want to check for 2 plus 1, my left subarray would be like this, right? So that is why it should be less than this particular value. So that when I do low plus 1 and I make this left subarray like this, I'm still left with one value on the right, right? So these are, again, I'm telling you, these are some things that will differ from implementation to implementation. That is completely up to you how you implement this code, but you will have to take care of these smaller things, that you leave at least one position for the second subarray, because there should be non-empty subarrays. Like, this is very important condition. So that is why when I am checking that low is less than I minus 1, I again calculate the value of PP and QQ. So this is very simple. I just added 1 to low. So if it was from 0 to low here, it is from 0 to low plus 1 here. And if it was low plus 1 to I here, it is low plus 2 to I here. So this is the same thing. I just added 1 to the value of low, right? Again, I do the exact same thing for the second half. So the second half will start from I plus 1 and will go till n minus 1. Again, high. I am setting n minus 1 as high because this value should never be true, and this value should always be true. Again, the same binary search. So this I'll leave this particular task for you as a homework to understand what I have written in this code. I'm telling you that this is the exact same thing that I have written previously, and this is the exact same logic that I'm using. And if you read this on your own, then you will be able to understand why I've taken these specific values. So again, I'm doing the same thing. I'm calculating the value of R and S. Now I want to calculate for low plus 1. That is why I will be storing in RR and SS. So whenever low is less than n minus 2, I am updating the value of RR and I am updating the value of SS. So I am checking this particular condition just to make sure that there is at least one element remaining at the end, and I'll leave this as a task for you to check how this particular condition will be able to check whether there is one element at the end, right? So again, I calculate my value of best as best comma maximum of PQRS minus minimum of PQRS. Now if the value of PP is not equals to 10 raised to power 18. So why I am checking this condition? Because I have initialized both of them as 10 raised to power 18, and only if this condition is true, I am updating them. So if the value of PP is 10 raised to power 18, that means this particular condition was not satisfied, and hence we cannot update, we cannot take this value of PP and QQ. So if it is not equal, I will take PP and QQ. R and S will remain as it is in both of the maximum conditions. Again, I'll check for R. If it is equals to 10 to the power 18, I'll update R and SS. P and Q will remain as it is, as I have discussed already in the explanation. Again, if both of them are not equals to 10 to the power 18, I'll take both of the updated values PP, QQ, R and SS in both of the max and min functions. So these are the 4 possible combinations that I need to test for every value of j, right? In this case, I have taken j to be I, so it might be a little bit confusing, but it's just the variable names. So after this whole complete for loop is executed for all values, what I can do is I can just return my best answer. So I can just return best. So this would be the solution for today's problem of the day, partition the array. I know, like, this question is actually a bit tricky, and you need to be very careful while implementing this, because even a single plus minus 1 difference can ruin your whole code and you'll be getting wrong answers. So I myself have been getting lot of wrong answers on this particular question due to these smaller implementation mistakes. So I hope that you guys were able to understand the solution. If you did, then please consider dropping a like on this video, and don't forget to subscribe to the channel. It's always free of cost, and if you don't find the videos interesting later, you can always unsubscribe. And share this channel with your friends. Till the next video drops, keep coding, stay safe, bye bye.